Great, good morning. So today we build on the topic all about how CPUs work. If you remember last lesson on the P strand, the principles of computer science, we introduced this idea of fetch, decode, execute, taking the magic out of how CPUs work and just relating it back to the fact that they just do this process over and over again repeatedly. Fetch an instruction, understand that instruction, and then run that instruction. Get the next instruction, understand that instruction, and then run that instruction. They do it over and over and over again. Today, we start off by being able to label that diagram of a von Neumann CPU. Last lesson, I think in P14, we had the diagram where you had all of the bits already given to you. This time, you haven't got those labels. You've just got to try and remember. So you can check back what you did last time. We want to understand what all of them do and how, so this is the most important part from your perspective, I suppose, is how you can make one CPU faster than another in terms of speed and pipelining. So a recap, so this is in the PowerPoint, you can access the PowerPoint, this is basically the answers to the first question. You've got your input device, like a keyboard or a mouse. You have your output device, like a screen or a printer or something. And then you've got your computer. The computer consists of a central processing unit, a CPU. Inside the CPU is the control unit and the arithmetic logic unit. And then the CPU sends and receives from the RAM, the memory unit. So this is a slightly different diagram to this one here. This is the CPU here, but we've still got memory down here, input, output, and then the control unit. The only other thing that this shows is a register here. So let's see if there's any more detail on here. Yeah, there we go. This is the detail that we need. So we have this arithmetic logic unit. It's shaped in the kind of shape of weird underpants, I suppose, like superhero underpants. Because it has one output, it saves its results into the general purpose register, the accumulator. Remember, a register is very fast but very small. It can only store a single value. So if the arithmetic logic unit has two inputs, like a 1 and a 3, the arithmetic logic unit can do whatever it wants with those 1s and 3s. It can add them. 1 plus 3 is 4, so 4 will get saved in the accumulator. Or it can subtract them and say 1 minus 3 is minus 2, and it will store minus 2 in the accumulator. Or it might be able to multiply them, or it might be able to compare them, or it might be able to bit shift them. All sorts of different arithmetic, maths, logic, comparing, manipulating, operations on the 2 bits of data that come in. And when I say bits, I don't mean zeros and ones. I mean 2 words of data, 2 values of data that come in. We have 2 registers inside the control unit. This one stores the instruction that we've just fetched from RAM. How do we know which one to fetch? Well, we need to know which one is the next instruction to fetch next. So when you switch the computer on, the program counter is set to 0. That means that 0 gets put on the address bus. The control unit sends a signal along the control bus. The RAM responds to the control bus, looks at the address bus to find that 0, because we want the first instruction at position 0. And then it will load what is at the first address at location 0 and put it on the data bus. It then travels along the data bus, so it can be stored in the instruction register. That's what we want to do first. We've fetched it. Now we can decode it. So decode basically just sends part of that instruction to the ALU, which tells the ALU what to do. Is it going to add or subtract? Or is it going to store something or load something? Is it going to send something to an output? Is it going to read something for an input? We look at that instruction register to work out what to do, and we decode it. Once we've worked out what we need to do, then we can execute it, which means the control bus sends a little signal to the arithmetic logic unit to say, right, do this, or do that. Or it will send a signal to RAM to say, load something, or send a signal to RAM to say, save something. And then you just increase the program counter by 1 so that you can get the next instruction. You fetch it, you decode it, and you execute it. You increase the program counter by 1, you fetch, you decode, you execute. Occasionally, the program counter doesn't increase by 1. So if you think about your Python code where you have if something is true, or for, or while, it's not sequential going from the top of your Python code to the bottom of the Python code in order. Sometimes you have a while loop which will go round and round in circles, or an if statement which will skip certain lines of code. If that's the case, then you'll have a branch instruction, and a branch is basically just saying change the program counter to something else so something else happens in your code. But that's how everything works. It's all inside that CPU. So what does the control unit do then? Well, it sends and receives signals to other parts of the computer system, like the input devices, the output devices, the RAM, so that everything is synchronized. It's all controlled. It responds to events, like when you press a key, and it synchronizes the whole fetch, decode, execute cycle. So the control unit, nice and easy, it controls stuff. Arithmetic logic unit, well, it can add, subtract, multiply, divide, compare. It can do and or not comparisons, check and see if things are equal. It has two inputs. It can store a value somewhere. It needs to know which operation, and it has a status, as in, are the two values the same? You don't need to remember all of these extra things. I just wanted to explain the values. That's the accumulator register where it saves the result. It can load values from two places, so maybe from the accumulator and from RAM. It gets its instruction from the instruction register. Remember, you fetch the value from RAM, you store it in the instruction register. That instruction register is going to tell the accumulator what to do. And status just means, well, if we're comparing values to check and see if they're equal, then we can set that somewhere. Okay, a little bit of terminology here. Your registers are known as immediate access storage. This means you can access them. You can access them in one clock tick. Registers are much faster than RAM. RAM might take maybe 10 clock ticks from the CPU to be able to access. They're much slower. The hard disk drive might take, I don't know, 1 million clock ticks. That's incredibly slow. So you want to store stuff as fast as possible, as close as possible, but you've got a limited amount of storage in your registers. So these are the three registers you need to know about for GCSE. Instruction register stores the instruction you are currently executing. The accumulator stores one value, which is the result, the accumulated result. It's the output of the ALU. And the program counter is the memory address of the next instruction. It's really important you remember. Instruction register is the current instruction. Program counter is the address of the next instruction, so that you know which one to get next. So I'm going to pause before we go through the clock. I would like you to have, what have I done with it? P14 from half term 3 open. It's input, it's output, it's RAM. 3 registers, can you remember what they are? And this is the ALU, do you remember what that stands for? Put your own labels on, and I'll pause you in a few minutes. So this question does say there's 8 things you need to label. So that's 1 of them, 2 of them, 3 of them. Then there's 3 registers. There's this thing here. The other one is the box around those 2 registers. Okay, so we're going to go through again what the fetch, decode, execute cycle looks like. We're just going to go to tanks.withcode.uk. We're not going to bother about controlling the tank. We're just going to stick with a normal little man computer. There are a variety of different simulators here. If you search for little man computer simulator, the one that most schools use is the one by Peter Higginson, which is this one. Where you can write your code in here, you can see how it assembles, and you can see all 99 storage locations. It's exactly the same as this. If I copy that code in, then hopefully if we submit it, this all gets assembled. So these are comments, we can ignore those. We just have something like imp for input, and you can see that instruction at address 0 assembles into this value 901, which is exactly the same as this one here assembling into location 0901. What on earth is that all about? Well, the instruction set for the CPU is basically a list of what the CPU can do. Our little man computer CPU can add numbers, subtract numbers, store numbers, load numbers, 3 different ways of branching, which is like how you do if statements or while loops or for loops. It can read a value in, it can send a value out, it can stop, or it can save data. A modern Intel CPU will have millions of instructions it supports, including highly specialized ones. This is as simple as it gets. You can't buy a little man computer CPU. They don't exist. It's an abstraction. We've hidden the unnecessary detail to focus on the most important thing, but it is a set of instructions that you need to be aware of for your GCSE, and we build on it for A-Level 2. So try to make this as easy as possible. Basically, you've got 99 spaces in RAM to store stuff. If you've got 4 gig of RAM on an old computer, that's 4 billion memory locations. You've got 8 gig of RAM, that's 8 billion memory locations. We haven't. We've got 99 of them. So it's a tiny, simple CPU. But it's enough to be able to do some simple instructions, some simple programs. Where does this 901 come from? Well, the instruction set means when the programmer types in low-level code, INP is short for input, and it means 9 something something is either input or output. So the 9 means input or output. If it's 9 something 1, it's input. If it's 9 something 2, it means it's output. The normal little man computer can only have one input device, as in it reads from the user. You type something in down here. I've just extended it a little bit so that you can have additional input for the tank, but we'll ignore that for now. So let's fetch, decode, execute. We'll step through. We've just done fetch. That means we look at the program counter to find an address. We put the address on the address bus, we send it across to the RAM, we send a control signal across the control bus, and we say, I want you to fetch the instruction at location 0, because 0 is in the program counter. Remember, the program counter stores the address of the next instruction. So at location 0 is 901. That 901 gets sent across the data bus and gets stored in the instruction register. That's fetch done. Next, we'll decode it. That basically means look at this value, work out what it means, and it means input. That's good, because that's what the programmer wrote. Then we execute it. So I'm just about to press step. I've pressed it now, and we've executed it. I'm going to put a number in. That number is going to get stored in a general purpose register, which is the accumulator. We've only got one general purpose register in this CPU. Real CPUs will have lots of different registers. Remember, registers store single values. They're very fast, but they're very small. So whatever I typed in goes in here. All right. At the end of the fetch, decode, execute cycle, the program counter is incremented, which means increased by 1, so that the next time I do fetch, we're not going to fetch from 0 anymore. We've already done that. We're fetching from the next instruction. Okay, so I've plopped a 308 in here. Where's 308 come from? Well, if you decode 308, we look at the instruction set, 3 something something means store. Store the value from the accumulator into the memory address something something. So when it says store 8, that assembles to 3, 8. The 8's come from the instruction, and the 8 is a memory address. Because look down here, this DAT0, that's a memory address. It's going to be stored at memory location 8. So let's step through, decode it. Yep, we want to store the value 55 from the accumulator into memory address 8. Good. And we've just done it. Can you see memory location 8 has now got 55 in? We've stored the value from the accumulator at that location. Okay. Next instruction, the mnemonic, the thing that the programmer types in is input. When the programmer assembles the code, the CPU has no idea of this stuff on the left-hand side of the screen. It only knows what's in memory. So we fetch the instruction from location 2, 901. We decode 901, which is another input. We execute it, and I'm going to put the value 1 in. I'll pause the video, and I'd like you to tell me what happens to that 1. Yeah, so that value 1 is going to get stored in the accumulator register. Notice the program counter has just increased, so the next instruction is going to be 301. Good, so we've just been discussing what 309 means. Let's check and see if we're right. When we decode it, it means store the value in the accumulator, 1, into location 09. So there's nothing in 09. Well, that's not true. There's a 0 in 09 at the moment. Bear in mind, when your computer switches on, it's random access memory. You've got no idea what's in RAM, so you can't assume it's all zeros. You have to load the contents of your RAM in from your hard disk when the computer switches on, because it stores random bits when you switch your computer on. So hopefully, let's see, we should now have a 1 at location 9. Jolly good. Program counters increased. Let's step. Okay, we haven't seen this one before. LDA 8. What do we think this is going to do? So what this is going to do, 508, means we'll look it up from our instruction set. 5 means load. Load from somewhere. Load from where? Well, load from 8. So we're going to look at memory location 8, find 55, and plop it into the accumulator. Let's see. It's just happened. Well done. All right, next one. Program counters increased. That means the address of the next instruction is at location 5 in memory. So we'll fetch it. We've just got 109 into the instruction register. Which bus did that value travel down? The value 5 travelled down the address bus because that's an address of an instruction. The value 109 travelled down the data bus from RAM back to the CPU because that's the actual instruction. Okay, so let's decode that 109. 1 means add. What are we going to add? Well, we're going to add the value at location something, at location 9, at location 9, at location 9. We're going to add whatever's at location 9, which is currently a 1. What are we going to add it to? We're going to add it to whatever's in the accumulator, so that's going to be 55 plus 1. Where are we going to store the result? We're going to store it back in the accumulator. So remember that the arithmetic logic unit looks like a pair of underpants, like triangular underpants, with 2 inputs and an output. One of the inputs is going to be from the accumulator. The other input is going to be from RAM. We're going to get both values, and the output is going to get stored in the accumulator. You ready? Let's execute. Good, we've got 56 in here. Okay, I'm going to pause in a moment. I'd like somebody to predict what will happen when I fetch the next instruction. Remember, the program counter tells us which instruction is next. So if the program counter stores a 6, when we get to the fetch stage, I'm going to look at location 6. What does that mean? It means I'm going to put a 6 on the address bus, send a signal to RAM to say I want to read from location 6. Let's see. So we've just fetched. We've put 6 on the address bus. We've sent a control signal to say read. RAM has responded by putting 902 on the data bus, and the CPU stored that in the instruction register. Now we want to decode it. What does 902 mean? Well, we look at the instruction set. 902 means output to device 0. So what will that do when we execute it? Well, something is going to be displayed. I'll pause. What is going to be displayed? So it should be the number in the accumulator, which is 56. Let's execute. Good. The tank has just said 56. All right. Let's go. Fetch. I want to fetch from location 7. Why? Because that's in the accumulator. What have I fetched from location 7? I've fetched a 0. And where have I put it? In the instruction register. What does 0 mean? It means stop. And when we execute it, notice the program counter does not increase. We've just stopped. Here's a Class Charts positive question for you. Why is it necessary to stop? So at location 8, the next thing is the data that we stored. Remember, this DAT is for data. This DAT is for data. Remember, we stored a value at location 8 and we stored a value at location 9. If we didn't have this halt, then the CPU would just go on to the next location and try and execute this. And that's essentially how viruses work. In a von Neumann processor architecture, data, variables, and instructions, your code, are stored in the same memory address space. If you can accidentally trick, or deliberately trick, your CPU into executing data, then you can make your CPU do whatever you want to do, even if you're not the programmer. That's basically how most viruses work. You inject malicious data in, you trick the CPU into thinking it's an instruction, because the CPU has no idea. Unless you tell the CPU to stop, it's going to happily continue and try and execute that data. There's nothing special that tells the CPU this is data rather than an instruction. It has no idea. Okay, why am I telling you all of this? Because back here, when it comes to pipelining, remember how slow this was. We've got just a couple of lines of code, and it took us about 10 minutes to go through all of this. Each time to execute, I had to press step 3 times, once for fetch, once for decode, and once for execute. Pipelining here means making sure that the execution pipeline is full, so it's trying to do as much as possible so that you can execute one instruction every clock tick. But that's not always the case. If I build up a table here, let's do something like this. Let's say clock tick. First of all, what is a clock? Well, a clock just means a signal that goes from 0 to 1, 0 to 1, 0 to 1 very fast. It's a signal that switches electricity on and electricity off, and it controls everything. It synchronizes everything. If you've got a CPU that runs at 4 gigahertz, it means that your clock is going on and off 4 billion times every second. But it doesn't necessarily mean that you're executing 4 billion instructions per second. Because in the first clock tick, the second clock tick, and the third clock tick, we need to know what's actually happening. First clock tick, you'll fetch the first instruction. But you've fetched it, you've not executed it yet, because before you can execute it, you need to be able to decode it, and that takes a whole extra clock tick. Oops, I'm decoding the first, not the second, the first instruction. And it takes 3 clock ticks before you can execute. If you had no pipelining, let's put this on a new page, otherwise it's going to be hard to see. Without pipelining, what you do is then do what we did on the tanks.withcode.uk. You just need to press step again to fetch the second instruction. Can you see how it's going to take 6 clock ticks before you've executed the second instruction? Can you see that? Execute. That's really slow. You're dividing your speed by a factor of 3. What you can do instead is say, whilst you are fetching the first instruction, there's not a lot else you can do, but whilst you're decoding the first instruction, you can fetch the second one. And then whilst you're executing the first one, well, wouldn't it be nice if you filled the pipeline up by fetching the third instruction? You're doing these at the same time. And whilst you're fetching the third instruction, you can be decoding the second instruction. It still takes 3 clocks to execute each instruction, but by the time you get down here, you don't need to fetch the second instruction. You've already done that. You can fetch the next instruction, which is the 4th instruction, because whilst you're doing that, you can execute the second instruction. And whilst you're executing the second instruction, have I done that right? Fetch, decode, execute. Yeah, I can decode the third instruction. Why is it called a pipeline? Well, think about a gas pipe. I can't spell and type at the same time. Instruction. If you think about a gas pipeline from Russia to Great Britain, if Russia decided to switch off the gas, then we'd still have something in the pipeline, but then the gas would run out. What you don't want to happen is like order a bottle of gas on Amazon and wait for it to be transported all the way from Russia to your house. You'd wait for weeks, wouldn't you, while it goes in a container ship. When you run out of gas, you've got to wait for another 6 weeks before you can put your heating on. It's rubbish. What you want to happen is as soon as you switch on your cooker or your boiler, there's gas in the pipe ready to go. So that's what pipelining means. This level of understanding is what you need for A-level. You don't need to understand that at GCSE. All you need to know is pipelining at this level means making sure that all parts of the CPU are kept busy so that you can fetch and decode and execute different instructions at the same time. So once you've written out your descriptions in this document, do save this. This is in topic 3, computers, if you're working at school. And it needs to get uploaded to half term 3, computers 1, please. Thank you.